Today we're going to be mapping out the electric field as part of our quest to discover how the forces of electricity travel across space and through time, how quickly one charge notices another charge is there and has time to react, where the electric field is strongest and weakest, is it safe to stick your fingers there, and will you get struck by a spark if you do. You wrote up yesterday in your notes that the definition of an electric field is the way a positive test charge would move. Well, here's a problem. If you had a positive charge right here, which way would it move? Down? That's easy. Draw an arrow, draw a vector going down. What if you had another positive test charge here? It doesn't see the first charge up here because that's only hypothetical. It's a test charge. It's not really there. If you have another positive test charge here, which way will it move? Up? All right, up. Draw in a vector and complete the picture. Which way would a positive test charge move if it were here? What about here? Draw those vectors too, and notice that you're following a certain set of rules. Stop when you run out of space and can't fit any more arrows in. Pause for everybody to draw. Resume when most people are pretty happy with their little sunshine. Conclusion. Which way do positive test charges move? First, obvious, positive test charge are going to move away from other positive charges. They're going to move towards negative. That's what you did in this picture. They're going to take the fastest available route. There wasn't any question in your mind that when you were here, you were going straight up. That is, you were going perpendicular to the surface. Fastest route in, fastest route out. The third rule is a little bit strange. Charges can go left, charges can go right. But the electric field is a set of directions as to which way the positive test charge is going to move. Now, any positive test charge can move to the left. Any positive test charge can move to the right. Sometimes you've got one way. Sometimes you get the other way. But the one thing you simply can't do is this. You can't go both ways. So, no particle can ever go in two directions at once. Two field lines will never cross. You will either go left or you will go right, but there will be no point at which you are standing on a corner with lines telling you to go both ways simultaneously. The electric field will arrange itself so that two field lines never cross. Head over to the simulator now. You will see a cloud of test charges. I wish we could have them here in the classroom to play with on the lab bench, but tiny little particles of static electricity are extremely hard to come by. I expect we'll have better luck with magnetism when we can use iron filings. In any case, there they are. All the little white flecks are positive. See what they're doing? Decide amongst yourselves what the charge on the yellow sphere must be and why. All in agreement? Fantastic. Well, they're all going in one direction. We can look at what's actually happening. We can check the direction that they're moving. Look at the menu. See? Field vectors. Don't copy this down, but check that inward means inward. You're going to add the arrows yourselves. Then go see the field lines. This is the map that you drew before. The map that looks rather like a sunshine. Below, the positive charge will move up, above the positive charge will move down, left, right. It's important to make these lines uniformly spaced, or as uniformly spaced as you can, because thanks to these three rules, the spacing of the lines, the line density, will show field strength. If you can't fit in another arrow, and your arrows are running across each other and you're out of space, that's because the electric field is very strong indeed. If you're out here and you can fit a pen or two pens or two fingers in between field lines, that's because the electric field is weaker. Check what we talked about yesterday. Is it true that the electric field is stronger near the charge? When you were playing with the wands and the ribbons last week and the week before, was it true that everything got stronger when you got closer to the edge and weaker as you got farther and farther away? Good. The map is telling us what it should be telling us. Let's look at that map again in 3 This is the electric field around one negative test charge. You added the arrows yourselves on your drawings. You checked that they were all pointing inward. Now, see what happens when you add more than one charge. Up in the menu here, you can choose 2 charges, figure out if they're both the same or different, and don't forget to check the middle. Check out this one little particle here. What's it doing? What's it doing? And why? The ones you guys are responsible for are the 2 charges, point charge double, you'll figure out the charges in no time. The dipole. Define a dipole. You can see one right here. Look at the way the charges are moving. Look at the vectors. Confirm which one is outward and which one is inward. Remember that. Then look at the field lines. Oh my gosh, is that cool or what? Look at it. What does it look like? Look at it all from all sides. See what it looks like at the back. When you're so close you can only see one charge. See what it looks like at the front. When you're so close you can only see the other charge. See what it looks like at the side when you can clearly feel the electric field being changed by 2 charges. These are the ones that you're responsible for drawing in number 1 and number 2. If you don't want to draw the 3D because it gives you a headache, you can choose from the 2D views. X direction, Y direction, or Z direction. There. That looks nice and drawable. Don't forget to add the arrows on each one of your field lines. You remember which one was out and which one was in. You do not need to draw this box here or the edges. Just draw the field lines. You want it in space, not restricted by the simulator. Now, there are plenty of other things you can play with. Once you've done a dipole, take a look at a quadrupole and see what happens with a quadrupole. What's a quadrupole? And hey, what's that building up in the middle? Right in the middle, in between the 2 of them. Check it out. What's it doing? You can play with a line, which is an electrical wire. That ought to be useful for something. That's 3D. You can play with 2 lines, also in 3D. What does that look like? Does it look familiar at all? If you like, you can make the field stronger or weaker. Check out the color code. White means strong, green means weak. You can add more field lines so you can see what's going on. You can move the lines further apart to see how that affects the field, or you can move them very close together. You can play with plates and make them bigger. You can go to your next item on the sheet, number 4, 2 parallel plates. Those are awfully small parallel plates. So once you've got them at a distance where you can see what's going on, why not make them bigger so you can really see what's going on in the middle? You want to pay attention to the top, the bottom, the sides, and the middle. What's going on in between those 2 plates? Which way are the particles going and why? What's the charge on each plate? How do you know? And what does that mean about the field? Those are the configurations you're responsible for in 1 through 4. If you have extra play time, there's no reason you couldn't look at some of what else is going on at this menu and see if anything interesting is going on. And if you want to draw something, you can also stop the display and see what there is to draw. At this point, you'll be in good shape to do number 5 as a team by hand. Follow those field line rules for the pointed rod. The wire you had in the simulator was infinitely long. It didn't have a back, it didn't have a front, and it didn't have any corners. See what happens with the corners as you draw evenly spaced lines perpendicular to the surface at all times. Don't forget the left side, don't forget the right side. See what happens, and see what happens to the field strength. What you notice about the field strength will help you answer the questions on the back. Happy playtime!